Hello, class. Welcome to today's lesson. Today, we'll look at exponential equations, and I've broken this into three cases. We're going to look at the first case, which is equations that have the same base. All right, but before we start that, this is what I want to say. When we are dealing with exponential equations, some of the skill set that I want you to bring to your understanding or to your forebears, you need to recall your rules of exponent. So, rules of exponent, because they become useful to us, kind of help us to break down problem set to make it easier for us. So, remember that if you have a to the m times a to the n, as a to the m plus n, a to the m divided by a to the n, that's a minus n. If you have ab to the n, then each of them gets raised to that. If you have ab all raised to the n, you have a to the n, b to the n. We also have a situation where you have a to the negative n is the same as 1 over a, and a over b to the n to the negative n is the same as taking the reciprocal raised to the n. And then obviously a to the 0 is 1. So these become useful to us if it helps us to clean up our exponential equations. The second one is, remember that we said that logs and exponential functions are inverses of each other. And by now you would have noticed that if your variable is a power, your best way to solve it is to convert it into what? Convert it into a logarithm and work from there. But don't be too quick to use that. If it's same basis, we can find simpler ways of doing that. So in today's lesson, hopefully by going through the three cases, you see when you need to apply maybe same basis technique or when you need to apply the natural logs. But I want you to feel comfortable in both ways. Sometimes it's easier to work with exponent same basis, and sometimes it is better to be in a log expression to be able to resolve that variable that you're trying to solve. So a quick reminder of some of the log properties that we looked at. Well, let's not get into that yet. I'll put that up later on. Okay. So let's look at the first example that I have. So case one says that if I have same base, as long as the base are the same on each side, or I'm able to get them to be on the same base on each side, then we are saying that the powers must be equal to each other. So let's look at the very first example. That's a rule. The same base raised to x equal to the same base raised to y, then we can assume that x and y must be the same power. So if we look at the first example, example 1, I'm seeing the same base. So I'm assuming these two other powers must be equal to each other. So I'm going to do 2x is equal to x plus 1. So x is equal to 1. And that checks out. You got 5 to the 2 is equal to what? 5 to the 1 plus 1. That checks out. Now let's look at the next example, example 2. So in example 2, you can see that 16, the base 16 and 64 aren't really the same base. So your attempt is to switch it to what? To switch it to a logarithmic expression because the power that we're trying to solve is a variable. But if you take a step back and you really look at 16 and 64, you notice that they have a common base, either base 2 or base 4. So I can see that I can write 16 to the x as 4 squared raised to the x, and I can write 64 as 4 to the cubed. So if I apply my rules of exponent over here, this really becomes 4 2x is equal to 4 to the cube. Now I have same base. I can pick the powers and set them equal to each other. So I get 2x is equal to 3. So x is equal to what? 3 over 2. Okay. And you can check it to see if it's right. Now let's look at the next one. So the next one, I have my really fancy base e, and both sides of the equation have the same base. So I can pick up the powers and set them equal to each other. So I get 1 minus 2x is equal to 3x minus 5. If we solve for this, we end up getting 1 plus 5 is equal to 3x plus 2x. So we end up with 6 is equal to 5x. So x is equal to 6 over what? 6 over 5. Alrighty. Now let's look at the next one. So if I look at the next one, I see a base 10, 2x squared minus 3 on the left, and on the right I have 1 over base 10, x squared minus 9. They are not the same because remember the rule is a to the x is equal to a to the y. So I can transform this a little bit by rewriting this as 10 raised to the 2x squared minus 3 is equal to 10. And if I return 10x squared minus 9 to the numerator, that becomes 9 minus x squared. Now I'm feeling comfortable because I have the same base on each side of the equal sign. So I can pick the numerators to help me solve this problem here. So I get 2x squared minus 3 is equal to 9 minus x squared, which if I put together now, I end up getting 3x squared is equal to 12. And I can divide, I end up getting 4. So I end up saying that x is equal to plus or minus 2. Okay. All right, so that does it for the first case where we had similar bases. All right. Now let's look at case number 2 where we have different bases. So when we have different bases, really you can compare. So your only alternative is to switch it back to a logarithm because we said that exponential functions and logarithmic functions are inverses of each other. And the variable that I'm trying to solve is a power. So I'm going to switch this exponential equation to a logarithmic equation. And so to do that, recognize that 3 is the base. X plus 2 is the power. And then 7 is the argument. So if you switch it, that is going to become log base 3 of 7. And that's equal to x plus 2. All right, remember that every log returns back to you an exponent. So at this point, I can solve this. This gives me log 3 of 7 minus 2 is equal to x. So that's one of the that's one of the answers that we have by just switching it back to back to a logarithmic expression. We can also kind of use our change of base that we learned last time and rewrite this as log 7 over log 3 minus 2, or if you prefer natural logs, then this is ln 7 over ln 3 minus 2. All right, both of them are all right, the same answer. Okay, now alternatively, which you probably see me do every now and then, is because of the properties that we learn in logarithms, I can apply the natural log, because if you recall that we had this law which says ln m raised to the n, I can drop the power down and have ln m. So we do have this property which allows us to drop the power down, and then it becomes much easier for us to work with the variable that we're trying to find. So alternatively, what I can do is I can apply ln on both sides. So I get 3x plus 2 is equal to ln of 7. All right, you could equally use your common log, which is base 10, to do it, but you see me using ln every now and then. And so now by applying that property, I can see that I can do x plus 2, and since it's 2 terms, I'm going to make sure I put that into parentheses. ln 3 is equal to ln 7. So my job is to solve for x, so I can divide by ln 3, which gives me x plus 2 is equal to ln 7 over ln 3. And then to find x is equal to ln 7 over ln 3 minus 2. Same answer as we found in the other way to do the problem. Okay, let's look at the next case. I have 8e, so let's number this. I forgot to number that. This is example 3. That was example 4. This is example 5. Now let's look at example 6. Okay, so to solve this, remember that the way we switch things to logarithms is you need to see the base, you need to see the exponent, and it's equal to the argument. Over here, I can't do that straight away until I divide. So if I divide everything by 8, I end up getting e to the 2x is equal to 5 over 2. Now, since I'm in base e, if I switch it to a logarithmic expression, that becomes ln 5 over 2 is equal to 2x. So x is equal to 1/2 ln 5 over 2, which if you apply your laws of logarithms is the same as you writing ln of the square root of 5 over 2. Okay. Alternatively, I could have applied the natural log on both sides after I've divided everything by 8. So I have e to the 2x is equal to 5 over 2. If I apply the natural log on both sides, now I can utilize that property to drop down the 2x on the left side. So I get 2x ln e is equal to ln 5 over 2. Now, ln of e, we know by now, is 1. So I am seeing 2x is equal to ln 5 over 2, which becomes x is equal to 1/2 ln 5 over 2. All right. What I don't want you to get into the habit of doing is doing ln 8 e to the 2x is equal to ln 20. Don't get into the habit of doing this. All right, that's a bad way to start learning how to solve equation utilizing natural logs. Always make sure that the coefficient on the base is 1. All right, so that you can apply the natural log on both sides. Let's look at the next equation. So the next equation shouldn't be a surprise to you. You've been working on this for some time when we're dealing with exponential functions. All right, and you had to do this kind of problem to solve for t. The best way to do that was to graph it and to find where they intersect. But now that we've done logarithmic functions, you now know how to convert things. So let's look at how things work. I think these are all 300. It looks like a 360, but that's just a 0. So to solve for t, it's a power, but I got to do a little bit of cleanup first so that I can be able to switch everything to a what? To a logarithmic expression or function. So I first got to get rid of the 300. So I have 1.025 raised to the 12t is equal to 1,000 divided by 300, where you can cancel these two. And so you have 1.025 12t is equal to 10 over 3. So I can apply my natural logs over here, ln on both sides, and then apply that property that allows me to drop the power down. So this becomes 12t ln 1.025 is equal to ln 10 over 3. All right. I like this because it allows me to practice on my logarithms, the rules of logarithms. So let's see how we clean this up. This becomes ln, oh well, let's set it up this way. So this becomes, trying to solve for t, so 12t is equal to ln 10 over 3 divided by ln 1.025, and so t becomes 1 over 12 ln 10 divided by 3 over ln 1.025, which if I try to utilize some of my laws of logarithms, the division tells me that I can write that as ln 10 minus ln 3 divided by my 112 outside, and then this is the same as ln 1.025. That's equal to t. Okay, so just anytime I get the opportunity to express things using my properties, I'm going to take that opportunity so that I'm constantly learning these properties and it becomes second nature to me. All right, let's look at the next expression. So the next expression says log or e, example 8. It says e log x is equal to 4. So recognize that it's just log x, meaning that we have a base 10 in that problem, okay? So first, I recognize that this is an exponential function. So I end up with e log x. When I switch that expression back to a logarithmic expression, I'm going to get ln 4 is equal to log x. All right. And then now let's see, how do we solve this problem now? I'm trying to solve for x. I need x to be all by itself. So I'm thinking of, how do I do this? Is there a property that allows me to get x by itself? Then you remember this property here which says that a base log of the same base of x is equal to x. So I think I can apply this. What I want to do is I want to raise each of the expressions into base what? Into base 10, because I'm dealing with the natural log, a common log. So I'm going to raise the left side to 10 raised to the ln 4 and raise the one on the right to 10 log x. Well, the expression on the right side, remember that it's got this invisible base 10. So that whole expression comes down to x, and then here I have 10 ln 4. All right, so that becomes the answer to that question. So the whole point is we are going back and forth using our properties and our laws, and then knowing that if I'm trying to solve an equation and the power is the power is the variable, then in some form or shape you might incorporate a log in your work. Okay. All right, let's look at the next one. Example 9. I have 5 raised to the x over 100 is equal to 2. The variable that I'm trying to solve is the power. So what I can do is I can either switch it to a log, or I can also apply the natural log or the log on both sides. So let me just make things interesting. I can apply the base 10, so I get log 5 negative x to the over 100 is equal to log 2. So in this case, instead of using natural log, I'm using our common log to solve the problem, which should end up with the same thing. So the property I can apply over here, as I see the power, I can drop the power down. I get negative x over 100 log 5 is equal to log 2. So I'm trying to solve for x. Negative x over 100 is equal to log 2 over log 5. And then if I try to solve for x, multiply through by negative 100 times negative 100. So we end up with x is equal to negative 100 log 2 all over what? Log what?